I'm Jeff Roos, a Senior Developer Relations Engineer at Intel, and this is Rolando, the Rendering Systems Lead at Epic. So what we'll talk about today is a little about why we're doing this. We'll go into a section about understanding the threading model of Unreal Engine 4, some of the CPU optimizations that we've done in the last year, and some GPU optimizations, and then wrap up. So why do Intel and Epic work together? Well, what we do benefits all games that use the engine. That's quite a lot. There's a lot of games in development right now that are running on Unreal. Unreal also runs on more hardware, from high-end Extreme Edition CPUs all the way down to phones. Intel is 81% of the PC CPU market as of the last Steam survey, so there's a lot of people that are running on Intel CPUs that also run Unreal Engine 4 games. And optimizations help everyone, from the high end to the phone. A lot of these optimizations are not specific to Intel hardware, and they could help competitor hardware and competitor CPUs as well. And some of the common goals we have with Epic is scalability means more reach and more available market. We want UE4 developers to have as wide a reach as possible to play on all kinds of hardware. And also, leading-edge APIs like DX12 are going to power tomorrow's games. So with that, we'll go into the threading section, and Rolando will tell you all about it.
Hi guys, I'm Rolando. Like Jeff mentioned, I'm the rendering systems lead. So I'm basically in charge of what we call the RHI. It's the render hardware interface. It's basically our abstraction between the low-level APIs, like the actual GPU APIs, like D3D, D312, Vulkan, and talking to the high-level renderer, so we don't have to write different code on the high level of the renderer. So I'm going to start by explaining a little bit the high level of how the threading model works in UE4. So you can see in this little chart, it's very abstract, but so we have the game thread, which is working on some frames. We have the rendering thread, which is slight overlapped from the game thread. So the game thread basically updates gameplay, animation, physics, networking, actor tickings. We have the simulation physics thread. So if you can see there, it basically can run a little bit overlapping the game thread, because it runs decoupled from the game thread, which is doing simulations. And finally, the other thread runs basically in the same frame as the game thread. We use a task graph-based system for distributing the work amongst the threads. And I want to focus a little bit more on the rendering side of it, because that's the area I'm in charge of. So conceptually, like I said, the game thread works on frame n+1, while the rendering is work on frame n, and there's some overlap of the work. So I wanted to add this little note for 4.22, which is the next release for next week. Commands for how do you tell while you're in the game thread that you want to run something on the rendering thread. We have this macro enqueueRender command, which allows you to put a lambda in the code, and then in that snippet you can see that function viewport begin render frame that actually gets run in the rendering thread, while the outer function, the enqueue begin render frame, runs in the game thread. So with lambdas also, the old system was just purely macro-based, so you can put a breakpoint in the middle of the body. With the new system, you can put a breakpoint in the lambda, so it's pretty nice for debugging. So how did the original rendering work in UE4? And I'll talk about basically the changes we've made and how it works now. So originally, we were in the rendering thread, right? There was some command, let's say A, which is allocate render targets. Then we would call D3D via our common API called like RHI begin render pass, which in the end calls D3D11 context OM set render target. And then we'd have more commands back in the rendering land, right? So we have calculated the uniform buffer. Then we call D3D set uniform buffer, et cetera, et cetera. So you can see in here we're overlapping basically interleaving the calls between the rendering and the RHI, or the D3D11 commands. So in order to get this more performant, we need to basically start recording these commands. So what we instead do is now enqueue them into a command list we call the RHI command list. So now we still are in the rendering thread called allocate render targets. Then we have that RHI command list begin render pass. All that does is enqueues the command into the list. It doesn't actually execute or call D3D11. So the next command, calculate view uniform buffer, same thing, get the command list, and then just enqueue the set uniform buffer command, and so forth and so on. After at some points that are clearly defined, or if the command list runs out of memory or points that are safe, we can then begin to start an execution. We call this a translation. So we translate the command list into D3D11 commands, and we start consuming them in this example on the rendering thread. So now we are consuming begin render pass, set uniform buffer, et cetera, et cetera. So now that this is decoupled, so just doing this change, you would think it's more work because you're basically adding the extra memory for the command list and just writing memory and then reading it back later on. But because of this, the rendering code is more localized as far as the code itself and the data is touching. Then when we get to the translation part, the RHI command list is also very small, very local. So we got better cache locality for both code and data. So just doing this change gave us about 5% CPU gains. So now that it's all decoupled, we can actually start moving it to another thread. So now we have the RHI thread, which we didn't have in the first image, the very first. So this is the new way of doing things. We have the RHI thread, which begins consuming the commands just like it did on the previous slide on the running thread, but now we're on an RHI thread. And same thing, we're just calling D3D directly. So the data is just basically accessing the command list and the D3D driver. And we just keep consuming the commands. So this is new for D3D11, and it's going to be in 422, thanks to our Intel friends here. So this is after this. This is a new version, I guess, of how it looks, the overlaps. So you can see how the rendering thread is slightly overlapped with the game thread, and then the RHI thread is a little bit delayed from the rendering thread. This doesn't add more latency, which it looks like it does, but it doesn't really. And by decoupling this way, we can also do other tricks. So we can do something we call the parallel front end, which is basically we can go wide when recording commands. So let's say we're in the middle of the base pass, or the velocity or the depth, which are the ones we can go wide. So we're in the rendering thread, and we're at a point where we can go wide. So multiple threads can start recording on different, basically auxiliary threads are working and working on areas of, it's like a subsection of the base pass, for example. So like you can see in parallel thread that's processing C and D. Those are not writing directly into the command list. It writes into a sub command list, which is like a smaller version. And the parallel thread E is also writing its own. So these threads can run in any order, right? B and then C, D, and E. So E could get processed before C and D. So the generation order is not guaranteed, but the translation order is because of the way we go wide and then come back. So the command list, you can see it's still in order. And then after we go on, we basically join the threads and keep going on F, and it's all in line. So, and then this is just to see how the RHI thread will be processing those. So as soon as A is available, it can start processing it and generating the D311 commands. And then after the join point, we can keep going and processing B, C, D, E, F. So we also have a similar trick that we can do on D3D12, where we can go parallel on the translation as well, which is one of the CPU optimizations we have. But I'll leave it to Jeff to talk to you about more exciting stuff.
Thanks, Rolando. So at this point, we'll dive into some of the CPU optimizations that we've done in Unreal. Lately, we've been working on some DX12 optimizations. We've been hearing plenty about DX12 for a long time, but adoption has been slow, and it's no wonder. Right, a performant DX12 engine is more than just a DX11 port. A lot of behavior we've been optimizing in the driver for DX11 is now up to the engine to detect and work around. With new features like ray tracing and variable rate shading, DX12 is becoming more and more attractive, but developers shouldn't have to sacrifice their performance to use these features. So we've been working with Epic and Microsoft on improving the DX11 or DX12 path in Unreal, as well as making our drivers more efficient. This includes things done to date include improving shader compilation times and speeding up our driver, and more work is ongoing. We've done plenty of other CPU optimizations, including some on a brand new system called Chaos. If you watched Epic's keynote or the tech talk just before this, you'll know that Epic has come out with a new system called Chaos, and we were right there with them helping optimize. We worked closely with them to optimize the low-level data solvers, the data structures, and thread parallelism. A lot of learnings came out of that. First of all, C++ is bad at SIMD. Different compilers give you different results, and it's hard to massage the data in such a way that you get optimizations every time. ISPC helps with that. So what we did is we integrated it into several places in this new Chaos system and saw roughly 3x gains. Another thing is that T-set can be bad in high-performance situations. So when you're doing intersection testing, like what happens in a physics system a lot, if you want, you have to do deduplication so you don't do a lot of extra work. Usually you use a T-set which guards it with a hash, so you can do tset.contains. We found that this was very slow in something that needs to be high performance like intersection testing. So using T-array, sorting, and then removing the dupes with remove swap from the tail is actually a lot faster than guarding it with T-set. The third thing that we learned is that parallel 4 can be overused. In some cases, we were doing thousands of jobs per frame, and it's a good way to cover up bad cache behavior using parallel 4. But in some cases, it's faster to go the single thread route and look at other optimizations. Batching can be helpful, especially if your data access patterns are cache friendly. So what is this ISPC thing that we put into Chaos? Well, the problem is that again, C++ doesn't cut it in a lot of cases. With games, you want to get every single ounce of performance you can. And CPUs since the early 2000s have had vector units that programmers can use to speed up their code. This is what's known as single instruction multiple data and gives you the ability to do 8 floating point adds in one instruction, for example. And that's what the AVX instruction set. One of the problems is that with C++, again, it's hard to get the compiler to vectorize anything. The usual solution is compiler intrinsics that you have to update with new instruction sets. So this is where the ISPC compiler comes in. The ISPC compiler stands for Intel Single Program Multiple Data Compiler. Yeah, that's a long name and quite a mouthful. But what does it give you? It gives you implicit parallelism in a language that looks like a shader language that runs on a CPU. Like a shader language, it assumes SIMD by default. And ISPC acts a lot like the GPU shaders that you're used to in the way that they're executed, but with some important differences that I'll discuss in a moment. One of the big benefits that programmers get when writing with ISPC is you can write once and compile to many other vectorized instruction sets, such as SSE4, AVX, or AVX2. If you're compiling for multiple instruction sets, there's an auto-detect mechanism that chooses the right function based on the user's CPU. So now you don't have to have multiple copies of your code around. No updating your intrinsics, and when a new instruction set lands like AVX 512, all you have to do is set the target and recompile. We use this a lot in the new physics system, and it will be available in UE4 soon. I think I heard 423. So the workflow here is that you include the ISPC module in your build CS to signal to the Unreal build system that you're going to use this, add ISPC files to your project, include a generator C++ header that serves as the interlink between C++ and ISPC, and then the Unreal build tool handles the rest, including compiling for several instruction sets and packaging up those object files into the final executable. And all of this was done to make it easy for Unreal developers like you all. So when do we use ISPC? It's good for dense compute-bound workloads, so heavy math things like physics intersection testing, cloth, or CPU vertex transformations, best with contiguous memory load, manipulate, and store operations. So for example, if you're using something like a T-array, it's great for that. It works best when there's no data dependencies between operations and very useful when combined with parallel 4 and batching especially. So remember I said it acted a lot like GPU shaders. Well, they do, but with some important differences. Whereas shaders all run independently, each SIMD lane runs one instance of the program. The difference lies in that ISPC runs all of the lanes in lockstep and are always guaranteed to converge at the end. So when you have branches that are not taking that particular branch of code, the SIMD lanes are turned off, and then they're turned back on when the scope ends. And that's faster than it sounds. One other neat thing is that this convergence allows you to do things like reductions across SIMD lanes. For example, if you're trying to find the sum of an array of integers, or the min or max, that's really, really fast. We use that quite a lot to make chaos physics even faster. So the bottom picture shows what ISPC code looks like and the assembly that it generates. What we have here is an RGB to gray that converts n values and stores the result using 3 multiplies and 2 adds. With AVX, you're running 8 of those at a time, and 2 of the multiply adds can be fused into FMA instructions for extra efficiency. The function below is roughly 8 times faster than a purely scalar implementation without needing to use intrinsics, and it's super readable, as you can see. So ISPC, if you're interested, there's a talk that Intel's giving that goes into more in depth there. But there's other CPU systems that we took a look at, including Cascade. We all know that Cascade is being replaced by Niagara slowly, but plenty of people are still using it. So we thought we'd show it some love. What we did was take a look at CPU particles inside of Cascade. CPU particles are great for enhanced realism over the usual GPU particles everyone knows about. They can do things like lighting the level, bouncing on complex geometry, and have complex interactions with other particles like gravity. They're great when paired with GPU particles in a single system to give that extra visual punch. So what we did was we improved the throughput of the CPU particles. Until now, you could only have a few hundred to a few thousand, depending on your system, and that's been improved greatly. The main problem was the physics engine that exists with locking the scene on reads, causing a serialization through a critical section. Separating reads and writes into separate locks fixed this problem. The second thing was that there was no existing support for ticking CPU particles in parallel. We used that by using critical sections when adding members to a non-thread safe T array, which is actually pretty rare as it turned out. And fixing both gave about a 4x improvement per frame on the number of particles you could have. And the patch is available for those that are interested in 4.19 and up. So one of the tools we use to track down these issues is vTune. We'll talk about that one just now. So vTune is Intel's CPU profiling tool. It's a good next step after Unreal's internal profiling tools have identified many of the problem functions. It helps to determine thread bottlenecks, sync points, and the way the work is given to the task graph on the CPU. For 4.19, Intel worked closely with Epic to implement support for ITT markers in Unreal Engine 4. And those are the markers that are used by vTune to get contextual data, and you can see that on the picture, I hope. So this added much needed data to the vTune graphical visualizations and was very beneficial in profiling the engine's thread schedule over some of our other 4.19 work. So we also used vTune on Fortnite to find that we're somewhat render thread bound. We're working with them on that too. And oh, by the way, vTune is now free if you hadn't heard, like really free. Yeah. Speaking of multi-threaded libraries, we have Embry. So Embry enables fast light baking for very good visuals using the light mask tool developers will be familiar with. It's used by default in static lighting builds already. So under the hood, Embry uses this ISPC thing that we keep mentioning. It supports all the way up to AVX 512 instructions, and we're working on getting those integrated into Unreal currently. Embry is fully enabled for multi-core, and Unreal Swarm even allows you to use other systems on your network to distribute lighting builds to speed them up. We have a nice quote from Daniel on the rendering team. So they saw some really good gains, almost 2.5 times faster lighting builds. So sensing a theme, we really like this ISPC thing for CPU stuff. Another thing we put into the engine is our texture compressor that also uses ISPC. So the ISPC texture compressor library sits on the back end of the cooking process, where you take the texture input you use to translate to, using in blueprints and translate it into something compressed that the GPU understands. Currently, Unreal uses the ISPC texture compressor to compress BC6H, BC7, and ASTC texture formats. Prior to integrating the ISPC texture compression library, ASTC, which is the newest and most advanced texture compression format used on Vulkan, would often take minutes to compress per texture. That's really bad if you're trying to iterate on a build. On the Sun Temple workload, the time it took to compress all textures went from 68 minutes to 35 seconds, with better quality over the reference implementation that was there before. So this is a 115x improvement. So this allows content developers to more quickly build their projects, saving hours per week of a developer's time. And this is an example of what it would look like. So you have the ASTC original on the left, the ETC1 encoding in the middle, and the output from ISPC texture compressor on the right. And this is for a 2K by 2K normal map. So now that we talked a little bit about our CPU optimizations, we can go into the GPU side. So one of the things that we want to do, and the mass occlusion culling actually bridges both boundaries, is we want to spend some CPU time to lighten the load on the GPU. The purpose here is to avoid sending occluded geometry through the graphics pipeline. So resolve queries on the CPU to minimize the GPU work and the latency. So what we have here is mass occlusion culling. It's a CPU-based low latency occlusion query system using a high Z representation. You basically render into a depth buffer using intrinsics, and we're converting it over to ISPC now to do queries against. It's guaranteed to be conservative with no false positives. The benefit here is, like I said, it reduces GPU time processing geometry that won't get seen anyway. You get results from occlusion queries during the same frame, and that's different than what Unreal does, which is it makes you wait a frame. So you won't see, if you're used to being on Unreal, sometimes you see like a white flash if occlusion is incorrect, and this will fix that. Also, it will work on your existing level geometry. You can send it your high complexity models, and it'll still work. But if you want it to be faster, it will benefit from having occlude meshes. And this is available as a patch. So how mass occlusion culling works is, first of all, you transform the triangles into screen space, you bin the screen by tiles, you clip the triangles into the bins, and then you run the tiles per task graph thread. So now that we've made sure that we're rendering everything that needs to be there, how do we ensure we're getting the quality out the other end with the performance you want? And Rolando will talk to you about that.
Okay, so now we're in GPU land. So sometimes you run your game, and you start seeing some frames starting to take a lot longer than others. Usually we have more content, we have particles, fog, smoke, have more draw calls, we have higher density objects. So our frame starts dropping or take longer, and then usually if your current frame takes long, then your next frame usually will happen too, because something happened, right? Like you said, an explosion happened, so that's going to take a few frames. You have a lot of alpha blending. So what can we do to mitigate that? So in 421, we added dynamic resolution. So basically that downscales the current scene render target to some values you determined, so that basically there's less cost. And this can be controlled by GPU timings, which is when you set that C bar that I hope you can see, or the dynamic res, that operation mode. So 0 means disable, which is the default, doesn't use dynamic resolution. 1 means use the game user settings, which can be set from the C++ side or the blueprint. And 2 means use the GPU timing from information from the last frame. So I wanted to show you these other 3 C bars, which are a little more clear than the other ones, just resolution-wise. So there's min and max percentage. So min obviously is how the smallest you can go, let's say 50% of the current size. There's also the frame time budget. This is the time in milliseconds for the previous frame. So once it hits that value, if it goes longer than that, then dynamic resolution will enter. And then max screen percentage, wanted to note that it's not necessarily 100%. It can be more, because if you have a high-end GPU, you can probably render at a higher quality. So how do you know if it's turned on? When you're developing, you can do stat unit in the console. Just press tilde and type stat unit. And when it's shown, it will show on the next to the units the percentage on the resolution, like X, Y, how much percentage of the render target is actually rendered into. If you need more information, you can just go to that doc or just Google Unreal Engine Dynamic Resolution. It's good that all our docs are public, so you can just search for that. If you want more detail, you can do stat unit graph. This shows you a little bit more of a chart. So you can see line 4 is the actual values of the percentage. You can see that hopefully you can see it, it hit 146%. So this is for a target of maximum 200, which is line 3. And then 2 is the target frame time in milliseconds. So you can see in point 1, those are the actual timings from the GPU. This feature was originally just working on console because the GPU timings on the CPU, on the desktop processors or the desktop GPUs are a little more quirky, but thankfully Jeff gave us a hand with that.
Thanks, Rolando. So what did we do with dynamic resolution? Well, we had something in our driver that allows applications to access the low-level hardware counters. We integrated that driver interface into Unreal Engine 4. And the thing there is, well, why isn't this a solved problem using API timestamps? You'd think, okay, you use D3D11 timestamp, it gives you the time it took on the GPU. Well, the problem there is that a timestamp is actually GPU plus CPU time, so it's the whole frame. We want just the time it took on the GPU to avoid the CPU bubbles. So if your CPU time spikes, what comes back is included in both. So what we did is we added, like I said, the driver API, and now we can get exactly how long it takes on the hardware so that we can drive dynamic resolution with some success here. And like Rolando said, this was previously only available on console, and now it's for the first time available on PC. Speaking of scaling down, we have a new hardware feature coming that does this automatically. So variable rate shading is something that we have coming up in our next generation of hardware. As real-time rendering engines become increasingly complex, we see a lot of games being pixel-bound on low-end hardware. Shading resources are wasted, creating pixels covered by motion blur or lost in the distance. Current techniques use a hammer to address this, reducing pixel shading by rendering the whole frame at a lower resolution, but then we're sacrificing visual fidelity. Variable rate shading is the scalpel as opposed to the hammer. Coarse pixel shading, now called variable rate shading, was invented by Intel in 2014 to allow game engines to adjust the pixel shading rate independently from the frame resolution so developers can spend time shading resources where they matter most. Here you can see the VRS techniques in action in Unreal's Sun Temple demo. In the scene, the pixel shader executes once for, yeah, that's the one I want. Here you can see the, the scene execute the pixel shader once for each 2x2 block of pixels. One of the advantages of this technique over raw resolution scaling like dynamic res is that the human eye is more sensitive to the outline of forms rather than their internal coloring. With resolution scale, those outlines may blur or deteriorate. Variable rate shading maintains the silhouette for higher visual fidelity. We've got a demo for this in the Intel booth, and we're also giving a talk with Microsoft, so come check it out. So now you're spending pixel budget where it matters the most. You're rendering everything you want to the screen. What's left? Anti-aliasing is left. Previously, your only two choices were TAA for high-end and FXAA for the low-end. What about something in the middle that's also good for text? So with Unreal, we're largely choosing between temporal AA and FXAA. Temporal has great quality, but comes with the usual blur and expense inherent in the algorithm. FXAA is cheap, sure, but it lacks the quality to make the solution tolerable, especially on text. So like any good developers, we found some more strange letters and numbers to add to the name, and we now have CMAA 2. So the first row of text is sharp, then to the right is the techniques applied. The second is anti-alias text, then again with the techniques applied. It's probably hard to see on this slide, but with CMAA2 you can see that they actually look pretty good compared to FXAA, and the performance is actually pretty good too. So the original CMAA has been around for a few years now. There's a pixel shader and a compute shader version. Last September, we published an update to the technique that's compute-based and that's even more performant. The intent there is to bring fast quality anti-aliasing to low-power hardware. Here you can see our implementation at work in Sun Temple. That's our edge detection there on the left. It's implemented through a series of compute shaders, and so this technique is not currently available in the engine, but again, we have a patch for it, which we're publishing. So we've talked a lot about a bunch of things that improve performance and help developer quality of life on both the CPU and the GPU. Go try out the things that we've worked on. We've done a lot of work here to help make developers' lives easier. If you have problems as Unreal developers, give us feedback on what we can work on next. Tell us about your pain points, and we'll go check them out. Talk back to us. Our Twitter handles are up there. So at this point, we have plenty of time for questions because I think we talked pretty fast. So please step up to the mic. We'll take questions, and I'll put up our samples and white papers. Also stick around. We're going to be giving a solid-state drive away and a couple other giveaways. So are there any questions? Thank you, by the way.